All right, let's talk about something you use every single day, from the moment you wake up. When you measure coffee, check the temperature outside, or see how many kilometers you have left on your commute, you're tapping into a hidden global network. You probably never think about them, but they're called SI units. That's short for the French Système International d'Unité, or the International System of Units. It's the most successful and widely used system of measurement ever devised, a true triumph of human collaboration. But to truly appreciate why they're so important, we need to take a quick trip back in time. For most of human history, measurement was a mess. Ancient units were often based on the human body. The cubit was the length of a forearm. The foot was, well, a foot. The problem? Not everyone's forearm or foot is the same size. A merchant in one town might use a different standard than a merchant in the next. Imagine trying to follow a recipe where a handful could mean something completely different depending on who wrote it. It was a recipe for confusion, disputes, and failed projects. This isn't just ancient history. In 1999, NASA's Mars Climate Orbiter, a $125 million mission, was lost forever. Why? One engineering team used metric units, while another used U.S. customary units like pounds and feet. The conversion error sent the spacecraft fatally close to the planet's atmosphere, where it disintegrated. Total chaos, right? SI units fix that. They provide a single, coherent set of definitions that everyone can agree on. The system is built on 7 base units. You know some of them already: the meter for length, the kilogram for mass, and the second for time. But there are 4 others: the ampere for electric current, the kelvin for temperature, the mole for the amount of a substance, and the candela for luminous intensity. Together, these 7 pillars allow us to measure and describe virtually everything in the known universe with incredible precision. But here's where it gets really beautiful. For a long time, some of these units were defined by physical objects. The meter was a platinum iridium bar, and the kilogram was a metal cylinder stored in a vault in France. But physical objects can change. They can be damaged, they can degrade, they can even lose atoms over time. So, in a monumental global effort, scientists decided to redefine the SI units, tying them not to fickle objects but to the fundamental, unchanging constants of nature itself. Many of these are deeply connected to the speed of light. Let's break it down. The meter? It's no longer a metal bar. It's now officially defined by how far light travels in a vacuum in the tiniest fraction of a second. Exactly 1 divided by 299,792,458. Because the speed of light is constant, the meter is now perfectly stable and reproducible anywhere. And the second? It's defined by the ticking of an atomic clock. Specifically, by the time it takes for a cesium-133 atom to oscillate between 2 energy levels over 9 billion times. This incredible precision is what makes technologies like GPS possible. Your phone's location depends on clocks that are stable, thanks to this fundamental definition. And the kilogram, the last holdout defined by a physical artifact, was finally redefined in 2019. Lagrange was retired. Now, the kilogram is defined using Planck's constant, a fundamental value from quantum mechanics. Scientists use an incredibly complex device called a Kibble balance to realize this definition, essentially weighing mass against electromagnetic force. And since Planck's constant relates the energy of a photon, a packet of light, to its frequency, even the kilogram is now fundamentally linked to the properties of light. So, in a way, every SI unit, the fundamental building blocks of all measurement, is interconnected in a beautiful cosmic dance. Let's look at how. The meter, our measure of length, is no longer a physical bar, but is defined by the distance light travels in a vacuum in a tiny fraction of a second. It directly links our concept of space to the universe's ultimate speed limit. The second, the heartbeat of our technology, is defined by the rhythmic ticking of atoms, over 9 billion oscillations of a cesium-133 atom, a clock so precise it enables technologies like GPS. The kilogram, once a metal cylinder in Paris, has been liberated. It's now defined by Planck's constant, a fundamental value from the quantum world, measured using an incredibly precise Kibble balance. The ampere, measuring electric current, is defined by the elementary charge, the charge of a single electron. We're literally counting electrons to define the flow of electricity. The Kelvin, our scale for temperature, is tied to the Boltzmann constant, which connects the energy of particles to temperature. We're measuring the average jiggle of atoms. The mole, essential for chemistry, is now simply a fixed number, Avogadro's constant. It's a specific count of particles, like a chemist's dozen on a cosmic scale. And the candela, measuring luminous intensity, is directly linked to the properties of light at a specific frequency. So you see, every single one of these units has a link to a fundamental constant of nature, many of which are understood through their interaction with light and electromagnetism. That's what makes the modern SI so powerful. They're not just arbitrary numbers. They're woven into the very fabric of our universe, as constant and reliable as the laws of physics themselves. So the next time you see a meter or a second, remember, you're holding a piece of the cosmos. If you found this as mind-blowing as I did, hit like and subscribe for more science made simple.